How do PID controllers manage complex dynamic systems? Imagine trying to keep a boat steady on choppy waters. The boat constantly tilts and shifts, but with the right steering, it stays on course. That's similar to how PID controllers work in managing complex systems. They keep things stable and accurate by constantly adjusting control inputs based on real-time feedback. A PID controller measures the difference between what a system is doing and what we want it to do. This difference is called the error. The controller then uses 3 actions to correct this error: proportional, integral, and derivative. The proportional part reacts immediately to the current error, giving a correction proportional to how far off the system is. If the error is large, the correction is big. If it's small, the correction is gentle. The integral part looks at the history of errors over time. It adds up all the past errors to correct any long-term discrepancies. This helps eliminate steady errors that the proportional part alone might not fix. For example, if a temperature sensor reads slightly below the target for a long time, the integral will gradually increase the control effort until the temperature reaches the set point. The derivative part predicts future errors by calculating how fast the error is changing. If the error is increasing rapidly, the derivative acts to slow down the system's response, preventing overshoot or oscillations. Think of it as a damping force that smooths out sudden movements, making the system more stable. In electrical engineering, PID controllers are used to regulate voltage, current, speed, temperature, and pressure. For example, in controlling the speed of a motor, the controller adjusts the voltage based on the difference between the desired and actual speed. This results in smooth acceleration and steady operation. Managing complex systems involves dealing with delays, nonlinear behaviors, and disturbances. The integral term helps counteract persistent disturbances, while the derivative anticipates rapid changes. The proportional part provides quick correction. Together, these actions keep the system stable and responsive. Sometimes, multiple PID controllers are used in a cascade setup. An outer controller manages a slower process, setting the target for an inner controller that handles faster changes. This layered approach improves control precision and response times. Tuning the PID parameters is key. Adjusting the gains for each part ensures the system responds quickly without overshooting or oscillating. Techniques like the Ziegler-Nichols method help find the right balance by testing how the system reacts to different settings. In summary, PID controllers keep complex systems on track by constantly measuring errors and applying proportional, integral, and derivative actions. This continuous correction process makes systems more stable, accurate, and responsive, which is why they are so widely used in electrical and control engineering.